So we're going to look at the 9's complement at this time. And the 9's complement is a strategy that was designed or discovered back in the early 1950s when we were working with computers, electronic computing devices. And those that were working with the computer trying to figure out, okay, how do we help the computer or the machine to do subtraction or perform subtraction, especially when it can't see. It can't see the numbers and decide, oh, these numbers, we should use shifting. These numbers, we should use menu and splitting. These numbers, we should use hop, skip, and jump. So the 9's complement is a strategy that was designed strictly for helping computers find differences, find subtraction problems, solve subtraction problems. So let's see how this method works. So we're talking about the 9's complement. It's really a very interesting, very clever computational strategy. It was introduced to me probably two and a half years ago by a good friend of mine. And we were making a trip to Nashville. And he said, here's an interesting subtraction strategy. So here's what you do. And then after he showed me the subtraction strategy, he asked me, so why does that work, George? What makes this computational strategy give you the right answer? But let's talk about the strategy itself first. Let's take a triple, two three-digit numbers. Let's take 364. Let's subtract 187. And once again, it looks like I'm always intentionally picking subtrahends so they have some digits that are bigger than the corresponding digits in the minuend. And yeah, I am. I want to make sure that here's a problem where you might have to borrow, but we want to find schemes, we want to find strategies, computational strategies that avoid the idea of borrowing, even though we talked about it when we looked at the value expanded form. So here's what we do. I'm going to take 364, which is the minuend, put it on top like we usually do. Take the 187, which is the subtrahend, put it in the bottom, and this is sort of like the idea we teach our kids, put it in this form. But when you put it in this form, we think we're going to ask them to borrow, but that's not what we're going to do. Okay, so here's what we're going to do. We are going to take the minuend and we're going to copy it down again, 364. Now, I'm going to modify the subtrahend, and here's how I'm going to modify the subtrahend. And here's why we get the name 9's complement. What I'm going to do to each of these three digits that are a subtrahend, I'm going to find out what their complement is with respect to 9. In other words, what do I have to add to this number to give me 9? Okay, so what is it that I have to add to the 1 to get 9? Well, that's an 8. What do I have to add to 8 to get to 9? That's a 1. What do I have to add to 7 to get a 9? That's a 2. And by doing that, I've changed the subtraction problem to an addition problem. And you're asking, well, why does that work? Then we'll come back to that. So I've got 364. I want to add to 812. And so this looks like 800 and 300 is 1100. And 60 and 10 is 70. And 4 and 2 is 6. So I get 1,176. And then I'm going to add 1 to it. Okay? You see, why are you doing that? Well, that was the part that this friend of mine says I was supposed to figure out. Why would you add 1 to this problem? So I add 1 to it, and I get 1,177. And then, all of a sudden, he said, now I want you to take the 1, and I want you to get rid of it. I want you to throw that away. And so once I throw that away, What's left behind is my difference. Now, is that the difference? Is 177 the true difference? Well, if I were to use shifting on this problem, go back up to the top of the screen. If I were to add 13 to the 187, does everybody see that's 200? And if I were to add 13 to the 364, 13, so that'll be a 7 here, that'll be a 7 here, that'll be a 3 here. So 377 minus 200, and sure enough, that is 177. So the 177 is the correct difference. It is the correct answer. Now, this looks like a lot of magic, a lot of hocus pocus to get to the 177. What is the computer really doing? If it's doing this arithmetic this way, why would anyone ask the computer to do this calculation this way? Well, for one thing, complementing with 9's, taking the digits in the subtrahend and subtracting them from 9 and putting their difference over here, the machine does not have to know what these numbers are. It just says 9 take away this number, 9 take away this number, 9 take away this number, and if this were a 9, 9 take away 9, 0, that'd be a 0. But it knows how to take things away from 9. 9's a good number in the minuend to take things from. We already talked about that. So let's go through another process or procedure that illustrates the 9's complement, and then we'll go back and see about talking about why does this strategy work? Why does this? Why do these steps? Why does this process lead us to the correct answer, to the right answer? So let's tackle another problem. So let's take a little bigger problem. Let's take 1,472, and let's subtract 895, and we're wondering if we take 1,472 objects and remove 895 objects, how many objects are left behind back in the minuend set after I subtract 895 from the 1,472? What's left? Okay, now I'm just talking about the process or procedure. Hopefully in the next few minutes we'll talk about why this strategy works. And again, this is the 9's complement. And remember, we're looking for strategies that aren't necessarily good strategies or best strategies. We're looking for different strategies because kids are different. They think and learn differently. They have different interests. They have different likes and dislikes. And so there may be a kid who thinks that, next to chocolate ice cream and soft butter spread on toast, that this is really a fantastic strategy. He or she might like it because of kind of the funny things that are going on here. And that's what we want to do. We want to grab the interest and boost their enthusiasm. So again, I'm going to do the same thing as I did before. Going to write down the minuend and the subtrahend, and it is a subtraction problem. Now I'm going to go through the steps that I did before. Now, watch carefully, okay? So the minuend, we just copy that down exactly as we had before. 1, 4, 7, 2. And now when I look down into the subtrahend, I see an 895. What you don't see is you don't see a 0 that's sitting just to the left of the 8. But it's there. We just didn't write it down. So I have to take the 9's complement with every digit that's underneath the minuend, including the 0 digit that's under 1. So if I'm looking at the digit that's under 1, it's a 0, and it's 9 complement. 9 minus 0 is 9. So there's the complement for the 0 digit. And then I complement 8 with 9, which means 9 minus 8 is 1. And then 9's complement with 9, 9 minus 9 is 0. And then finally, the complement of 9 with 5. 9 take away 5 is 4. So I have taken the 895 and I've written down the 9's complement. So the 9's complement of 895 with respect to the minuend, which has 4 digits, is 9104. And now, remember, we were changing the subtraction problem to an addition problem. So this becomes what? 10,676. And then from out of nowhere, we're told to add 1 to this. So out of nowhere, we add 1 to this. This gives us a 7, 7, 6, a 0, a 1. And then out of nowhere, we're told to look at that leading digit and throw it away. So when we throw that one away, what's left behind is 677. Now, I'll leave it to you to verify that 677, verify using another strategy, another computational strategy for subtraction, to verify why the 677 is the correct difference between 1,472 and 895. Of any of the previous strategies we looked at. What I want to talk about now is why does this strategy work? What is it that we're doing with this computational strategy? Why does it work? Why does this number that pops out here at the end after I do 2 or 3 funny things, which is what? 9's complement of the subtrahend, then add these 2 numbers together instead of subtracting, then add 1, and then throw this digit away, this leading digit away. Why throw that away? And I get down to what is supposed to be the answer to this problem. Why does this work? So here's what we want to do. I've got a minuend, and I've got a portion, which I'll call the subtrahend, that I'm going to remove. And when I finish, that gives me a difference. So here's what we're going to do. We're going to modify this problem to help us see what's going on. So I'm going to take the minuend and I'm first going to add 1,000 to it. Now, if I add 1,000 to the minuend and I don't add the 1,000 to the subtrahend like we did earlier when we were using the shifting method, then that means that I've increased the difference size by 1,000. So if I add 1,000 to the minuend and I'm going to subtract s from it, without the 1,000 it gave me the difference d. But if I add 1,000 to the minuend, then when I subtract s from it, I'm going to get the difference plus another 1,000 more. That makes sense? Okay, now I'm going to take the 1,000 and I'm going to split it up. Remember, numbers that have 9's in them make good minuends. So since I'm writing down this on the whiteboard, you can go back and look at it later at your leisure and find out, is George doing something that's not right or crazy. But again, I added 1,000 to the minuend set. I didn't change how many I was going to remove, and because of that, the difference will no longer be the original difference, but it'll be the difference plus 1,000. And I took the 1,000, split it up into 999 plus 1, and the reason for that is it's a nice number when it comes to subtraction. So I can subtract s from 999 plus the 1. So what am I going to do with that 1 that's sitting there? Well, I'm going to take it to the other side. I'm going to subtract, since the 1's sitting over here, I'm going to subtract it from both sides. So over on the right-hand side, I've got the 1,000, but I took 1 from both sides, so I'm going to subtract 1 from this side as well. So everything I've written down here from an algebraic perspective is equal. But again, notice what I'm doing. I'm modifying the minuend. I'm splitting the minuend up into 999 plus 1 because I want to subtract I want to subtract the subtrahend from it. And I split it up into 999. And the 1 that's there, I took to the other side, so I subtracted 1. So I should have added 999 to this side and added 999 to the right-hand side, and maybe it would have been easy for you to see. So here we're looking at this problem. So I've got a problem where I took the minuend and I subtracted the subtrahend, and I want to get to the difference. But I want to do it in a clever way. So what did we do? We wrote down the minuend, and we did something to the subtrahend. What did we do? Well, look right above here. I took 999 and subtracted the subtrahend from it. Well, that's finding 9's complements to each of the digits. That's taking the in this case, the hundreds digit, subtracting whatever was in the hundreds digit there. And then here's the tens digit, subtracting the tens digit from that. So I actually take all the digits in the subtrahend and modify them. So I'm actually taking and writing down here underneath the M, I'm taking 999, subtracting S from it. And notice this operation right here, that's addition. So I'm taking the original minuend, and I'm adding to it 999 minus the subtrahend. So this is the step that I'm completing. It's the addition step. It's doing the step that's on the left-hand side. So now what happens? When I add these together, I get what we're supposed to get. I'm getting M plus 999 minus the subtrahend. I'm adding those together, and then out of the clear blue, I add this 1. Well, when I add this 1 to it, notice what it does on the right-hand side of this expression. If I all of a sudden decide to add 1 to this, then it adds a 1 over here. So the minus 1 and the plus 1 becomes 0. So this difference is really the difference plus 1,000. Which means when I add this together, what I'm getting is the true difference plus 1,000, which means I have to get rid of that leading digit to get me right back to the original difference. So that's why I remove that leading 1 that's sitting out there. I'm getting rid of it. Now I did this as if the minuend were a 3-digit number. If it were a 4-digit number, I would add in 10,000. If it were a 5-digit number, I would add in 100,000. If it were a 2-digit number, I would add in 100. So this is if these two numbers here happen to be 3-digit in size. But that illustrates why this cute little looks like magic kind of works. I just modify the minuend on the front end to change the subtraction problem to an addition problem, as I did here, indicating with this red circle. And then when I got finished, I knew that I was 1 too short, so I added the 1 in. That got me back to the difference plus 1,000, and now I'm 1,000 too big, so I get rid of the leading number out there, and that gets me back to the true difference. So I cleverly, or those who designed this algorithm back in the 1950s, cleverly get to the difference of two numbers by changing subtraction to addition, adding a 1 at the appropriate time, after I did the 9's complement on the subtrahend, adding a 1 at the appropriate time, and throwing away the leading 1. Works all the time. very slick way. And this is called the 9's complement. So we've looked at a number of different computational strategies to find the difference set when we're finding the difference of two numbers, the minuend with the subtrahend. And they're all, very interesting, and they're just looking at ways to find the difference set, the difference, so that, kids have a variety of ways to look at, to form the calculations, and they're interesting. And they'll gravitate to whichever one they're more comfortable with. And so now we're getting ready to turn to the computational strategies for the arithmetic principle called division. Remember, there's two kinds of division, parted division and quoted division, and we're going to look at that in our next video segment. Thanks.